it's 9:31, so I think we start our morning session today. Welcome everyone. I hope some more people will join in a moment. Our first speaker is Giacomo Rosati, and you have 25 minutes plus 5 minutes question time. So please try to be in line.
Thank you everybody for the opportunity to present this work together with Giovanni Amelino Camelia and Susanna Bedic. And this work that we did is called Testing Curvature-Induced in Vacuum Dispersion with Gamma Ray Bursts. So let me start with some motivation and hypothesis. So, well, the main motivation is phenomenology of quantum gravity, and the hypothesis is that starting from fundamental approaches, the scale at which our description of space-time should be radically different is the Planck scale, which is the characteristic scale of quantum gravity, which is 10 to the minus 33 centimeters. And to this scale, as can be appreciated by different methods, but for instance, the standard Heisenberg microscope, it corresponds to a huge energy scale, which is the Planck energy of about 10 to the 19 gigaelectron volt over gigaelectron volt. Particularly interesting for the phenomenological hypothesis from the interpretation of quantum space-time is the possibility that this length scale corresponds to a minimum length under which no measurement can be performed, or analogously to a maximum energy scale represented by the Planck length, or approximately the Planck length. And even more interesting is the possibility that this maximum energy scale enters in the description of relativistic kinematics by a modification of the dispersion relations of relativistic particles through some extra terms here that are proportional to the energy and triggered by the Planck length. This is a description to first order in the correction, and in particular, in some of the models, it is interesting the case for which massless particles like photons, or well, in the approximation of ultra energy relativistic particles, travel at a speed which is different from the speed of light, the correction being proportional to the energy of the particle and triggered by the Planck energy. Basically, two alternative scenarios, if this modification of relativistic kinematics is indeed taken into consideration, are viable. One is the so-called Lorentz invariant violation, where the scale is essentially relativistic symmetries like Lorentz symmetries, but also translations or rotation, can in principle be broken at this scale. Well, usually it's Lorentz symmetry alone. The other perspective is the more recent proposal. Well, now it's more than about 20 years proposal of the form that essentially the scale of modification of relativistic kinematics is an observer invariant scale, and this is called the formation of special relativity. And the theoretical framework, well, the most studied theoretical framework for this kind of one of the most studied theoretical framework for this kind of analysis, and especially for the possibility of having a vacuum dispersion, is based on the mathematical structures of kappa Poincaré and kappa Minkowski non-commutative space-time. So in most of these scenarios, the relevant effect of in-vacuum dispersion can be characterized by a correlation between energy and time delay of the particles observed. And that's the basis of the work that I'm going to describe. So what does it mean testing in-vacuum dispersion with gamma ray bursts? So the first proposal of this kind of phenomenology dates right before the year 2000, and essentially, if we consider two photons emitted simultaneously from a distant source, like a gamma ray burst in this case, one expects that the two photons of different energy travel with a speed which is different proportionally to their energy. Okay, so one expects to observe this particle to arrive at two different times. In this picture, we have a low energy photon, which is depicted by a red straight line, and a high energy photon whose speed is slower than the speed of light proportionally to its energy and triggered by the Planck length, and arrives at some later time. Then the time of flight, which is of cosmological order, acts as an amplifier of the tiny Planckian effect, so that and the energy, of course, of the characteristic gamma ray burst, which in some cases ranges up to 10 to hundreds of giga-electron volts, so that essentially the tiny Planckian effect is compensated by the time of flight, so that it can be within the precision of observation of our available telescopes, like Fermi, for instance. Of course, since the travel time is cosmological, one needs to include in the picture the contribution of cosmic expansion due to the actual cosmological model, like for instance lambda CDM, and essentially this. So one has to replace the time of flight with a distant factor that depends on the redshift, and this is the formula that was proposed after several steps by different authors like Ellis, Mavromatos, and others, and then was finally devised in this paper by Jacob and Piran in 2008. And these are the cosmological parameters of lambda CDM, and this is the distance factor depending on the redshift that has to be put in this formula here. So then in 2009, this gamma ray burst that was detected by Fermi, the famous gamma ray burst 090510, that is a short gamma ray burst with a very high precision of detection, was able to constrain the scale of the effect up to the Planck scale, okay, by considering that this high energy photon single event here was detected in approximately in coincidence with the peak of the low energy emission of the gamma ray burst. Okay, so according to this, one was, and to the precision of the measurement and to the characteristics of the gamma ray burst, this experiment was able to put bounds which are, it has proved to be able to constrain this kind of effect up to the Planck scale. Okay, which something that was unbelievable until up to the mid 90s. So this experiment itself was the first strong evidence that quantum gravity phenomenology is viable. Considering the strong bound provided by this gamma ray burst, still it makes sense to test in vacuum dispersion statistically. What does it mean? That now we treat this data together with the other data from the other relevant gamma ray bursts for this kind of analysis. And this kind of procedure was proposed by the group of mine collaborators starting from 2014. And then we have considered it together with Amenio Camelia, Giacomo D'Amico, and Nicola Loré in a paper of 2017 in combination with a similar analysis we made for astrophysical neutrinos. And so basically, the idea is to take a phenomenological model for this time delay, where we also consider an intrinsic time lag at the source of the emission, and we rescale the energy by this distance factor in order to have a linear relation between the time delay and the energy, and we study the linear correlation between time delay and this rescaled energy. Okay, this is the idea. Then we have to impose some criteria of selection for the data, and in order to reduce the contribution of the background, we choose cutoff of the energies such that, well, in our work, we choose a cutoff such that the emission, the energy of emission of the photons should be greater than 40 gigaelectron volts, and take as delta t the difference between the high energy photon arrivals and the first peak of the low energy signal of the gamma ray burst. What we find is that of 11 data which are relevant for this analysis, out of 11 photons are compatible with the same, roughly the same value of the Planck of the parameter triggering the effect, okay, which is something like tenths of Planck length, of Planck energy. Tenths of 1 over Planck energy, and the correlation is also surprisingly high. But the most important ingredient of our analysis is what we call the false alarm probability, which is essentially we simulated the background by randomizing the times of all the data, and we made a huge number of simulations and calculating how many times the background data, the random data, can have a correlation higher or as high of the one of the real data, and this happens only in roughly in 1% of cases. So at least the data are still not so many, but the behavior it shows some interesting significance. So this was the analysis, and finally we combined this analysis also with a similar analysis for the neutrinos, and the also interesting result here is that roughly the same scale of the effect seems to be compatible over a wide range of energy, ranging from tens of gigaelectron volts characterizing photons and hundreds of teraelectron volts characterizing the astrophysical neutrinos detected by IceCube observatory. So this was the analysis we did before, and now I start with this new work that I present that regards only the photons part. Sorry, I have to close this. Well, so so until now, all these studies have been based on quantum gravity effects that are present also even in absence of space-time curvature. What does it mean? That I will explain it in a second. However, let me first stress that some theoretical considerations and some hints suggest that it may likely that the same quantum gravity effects could be triggered by curvature. What does it mean? For instance, the idea is that the possibility that the interplay between the cosmological constant and the Planck scale and the Planck scale of the effect, the cosmological constant characterizing the cosmological horizon and the tiny scale characterizing in a sort complementary horizon on the other side, which is the quantum gravity scale, like for instance was suggested by this work of Rovelli and Bianchi in 2011, could produce an effect which disappear when the cosmological constant is set to 0. Okay, so it doesn't survive in the flat limit of the formation of symmetry. This is what we mean by curvature-induced effect. And also this may have, well, for instance, in this work by Rovelli and Bianchi, this was connected with the introduction of a quantum group deformation of the kind of Q deformation, where this is the parameter of deformation in 3+1 dimension quantum gravity. And this is a deformation typical for those who are absent of these algebras of what is called Q de Sitter non-commutative models. Also, it was also argued in his previous works by Melino-Camelia, Smolin, and Starodubtsev of 2004 that in order to disentangle in 4 dimensions these quantum gravity effects from curvature, one essentially it seems that one requires some fine-tuning, which is very ad hoc, let's say. So it seems more likely that this effect should be triggered by a factor which is proportional to both Planck length and cosmological constant. So also there is this other proposal reason from Aspieri, Borowiec, and Paco that reach similar conclusions starting from non-commutative differential geometry applied to Drinfeld twist deformation in Kappa-Minkowski, for those who are interested. So this is the theoretical premise, and well, this encourages to consider a curvature-induced scenario where essentially, as I say, the Imbaco dispersion is not present in the flat, even if non-commutative limit, but only when sparsity and curvature is significant. Well, phenomenologically, it may seem hopeless due to the double suppression of space-time curvature and Planck scale. Let's see if this is the case for our toy model. So what we noticed is essentially that it's true at the first sight, but actually curvature appears in the formula for the propagation of particles, always multiplied by the distance traveled by the particle. Okay, so this is a good sign for for obtaining some kind of phenomenology of this kind. So since for the relevant phenomenology the distance is cosmological, this can compensate the space and curvature suppression. This is our expectation. So essentially, we started from the Jacob-Piran dispersion relation, that is the one which is related to the Jacob-Piran term for the time delay, which is the only one that was used so far in the literature. And let me describe it shortly. So the dispersion relation, the relation between the energy and the momentum of the relevant particle, is characterized by this modification term. This was obtained in the Lorentz invariance violation scenario. So this is the modification term, and what happens is the momentum of the particle is divided by the scale factor of the Friedman-Robertson-Lemaitre-Walker expansion metric. And so this was the ansatz of Jacob and Piran. And of course, this is the Hubble parameter, which is depending on the parameters of the lambda CDM cosmological model. And starting from this, you obtain the Jacob-Piran ansatz for the time delay. Now, I mentioned this our previous paper with Melino Camelli, Antonino Marciano, and Marco Matassa from 2015, where we actually studied the possibility of having, in general, Planck scale modified dispersion relation in Friedman-Robertson-Walker spacetime, both from the Liv and from the DSR perspective. And we obtained already a generalization of Piran-Jacob formulas that actually are present in both scenarios. In this here in the Liv, it is with this lambda parameter. Here it is this term with a beta pi gamma parameter in the DSR case. And actually, we obtain also other terms depending on the parameterization of the dispersion relation. Well, I will not spend time on explaining these new terms that we obtained, but I want also to mention some other papers. So a different kind of dispersion relation was already suggested by Piran and Rodriguez Martinez itself in a paper from 2006, and also there is this recent analysis by Pfeiffer, where he also studied the possibility of having other kind of Hamiltonian and dispersion relation related to time delays. And so, starting from however, from our result here for Lorentz invariant violation, we have considered the terms in this formula that can provide a kind of model that could describe what we intend as curvature-induced effect. So, if we consider now essentially this other term in the formula, this other parameterized term here, where essentially these redshift terms appears in the denominator, and we consider a toy model that combines essentially these two formulas in this way. So essentially, we consider we turn off these two parameters and we just keep these two in the time delay that we have found in this previous paper. We obtain this dispersion relation here, where essentially the only thing that changes is the position of the scale factor respect to the momentum in the modification term of the on-shell relation. So if one now studies the particle velocity starting from this on-shell relation, one obtains these scenarios, okay, where one has the standard Friedman-Robertson-Walker velocity here, and this deformation part, which is proportional to a constant term plus a term which is proportional to the redshift, okay? Well, for small t, one can show very easily that this reduces to this also standard part, which is the speed of a particle essentially in a de Sitter spacetime where this is the Hubble constant, and a part which is a deformation which is proportional to a constant term plus the Hubble constant here, so the Hubble parameter now measured now and this other parameter. So one notices that if one takes lambda prime equal to minus lambda, then this term here disappears, and the modification of the velocity essentially is triggered by the curvature term itself, parameterized in this case by the Hubble constant. So when the Hubble constant...
Sorry, you have 3 minutes. So
okay.
Try
Sorry.
to conclude.
So, so this is a case of curvature-induced correction. Then one derives easily the corresponding time delay formula, and this is what we obtained. Okay, this is the time delay formula for the curvature-induced case. Okay, this is my last slide, so I will probably be on time. And so now we consider again the same analysis for photons that was proposed by these my collaborators, and then in our paper in combination with the neutrinos analysis. These are the set of events of gamma ray burst photons that we have taken into consideration. First, let me recall what happens with the Jacob-Piram formula. If I plot them, I see that as I mentioned earlier. So now I plug the arrival time essentially minus the time of offset respect to the redshift of the source. And what we see is that it is true that 8 of our 11 photons fit well with the behavior, okay? But still, at the same time, 3 out of 11 do not fit the model, okay? Essentially, this one, and this one. Now, for this photon here, apart from the uncertainty, which is quite large, the time delay is larger, so it can be explained as considering that this photon may be emitted by a later peak of the gamma ray burst. This photon here has a smaller delay, so it cannot be explained in this way, but still the uncertainty is so large that it cannot be really, it is not so challenging for the analysis. This is the point which is very challenging, because this exposure shows a smaller delay and very small uncertainty, as I explained here before. So now, what happens in the case of the curvature-induced effect? So this is the behavior that we found from the best fit of our model. Okay. So what are the considerations that we obtain for the curvature-induced effect? We show that, first thing, we show that we don't observe a suppression effect due to the double suppression of curvature and Planck scale at redshift higher than 1. Okay, so the phenomenology is viable. Okay, there is no, as we have thought, the time of the distance of the sources compensate the suppression due to the curvature. However, one observes also, as one could have expected, a much weaker in-vacuum dispersion only for small redshift. And this feature is what makes essentially the model handle well the most challenging data that is represented by 09, 05, 10. So this is, so let me conclude. Of course, the effect could fade away considering more data, but we have shown that phenomenology of curvature-induced in backward dispersion is viable. And of course, was just a toy model, but we expected some features like the slow onset of effects at small redshift, which is the interesting feature that makes the model fit well with this gamma ray burst. Should be a general feature of this kind of phenomenology, and should characterize other scenarios covered that trigger quantum gravity effects. So this is all. Thank you for the attention.
Thank you, Giacomo. Are there any questions? We have a little couple of moments for the questions. Yes, Jose Manuel, please.
Hello. Hi, Giacomo.
Hello.
And nice talk. I just wanted to ask, with this scenario of curvature-induced, or with the standard scenario without curvature-induced, you have similar formulas for the Lorentz invariant violation and the SR case. Is there a way to distinguish between these two scenarios with this kind of measurements?
Yes, thank you for the question. So in this case, we had just consider a formula that we have obtained in the Lorentz invariant violation case, and essentially just as a toy model. So if at least according to our previous analysis that we presented here, we have this parameterization of time delays for the Lorentz invariant violation, which is quite straightforward to obtain from the dispersion relation. Essentially what happens, we have obtained also a competing formula for the time delay in DSR, even if it's a bit more complicated because you have to handle the relative locality which is present in this kind of scenarios. But at least for this phenomenological analysis that we have, these formulas that we have obtained here, what happens is that the Jacob-Piran case is present in both scenarios, Lorentz violation and DSR. But as soon as one gets away from the Jacob-Piran formula, so Jacob-Piran formula here is this term. Is this term here in the DSR case. As soon as one take other terms of the formula, so tries to do, for instance, the curvature-induced model also for the DSR case, then the formula that we have obtained are different. Are different respect to the ones that we have obtained in Lorentz invariant violation. So they coincide only for the Jacob-Piran case, but also because the Jacob-Piran case is a very special case of this formula, but which is, if I can tell you very shortly, is the case where translation symmetry is untouched. Okay.
Mm-hmm. Yeah. But do you think this would be distinguishable?
Yes. So the answer is yes, but yes, it should be distinguishable. But the prediction of the time delay, it's a bit to obtain it. It's a bit the machinery is a bit complicated, so one has to be sure that it's properly obtained. Okay. Mm-hmm. So as far as these formula are reliable, they are distinguishable. Okay.
Okay, I'm sorry, we reached the end of the time for your talk. Thank you, Giacomo. And the next speaker today is Mr. Mithya Friedman. If I pronounce, yes. Okay, good. Could you please try to share your screen, and once we see your screen, you can start.
Okay. Can you see the screen?
Yes, but please switch to full screen mode. Right. Okay, good. Please start. You have 20 minutes plus 5 minutes question time.
Okay, thank you very much. So my work has been done in collaboration with my supervisor, Dr. Soria Das from University of Lethbridge, Gaetano Lambiase from University of Salerno, and Dr. Elias Vagenas from Kuwait University from Kuwait. So, and in our work, we are trying to explain the observed Barium asymmetry in the universe using the generalized uncertainty principle. So here is a brief overview of my talk. First, I'll give a few motivations and goals for this talk. Then I'll proceed on modifying the Bekenstein-Hawking entropy using the generalized uncertainty principle. And then by using that and the holographic principle, I will show you how we modified the Friedman equations, not related to me. And then using the Friedman equations, we will then try to explain the Barium asymmetry in the universe. And at the end, I will summarize with concluding remarks. So let's start. The asymmetry between matter and antimatter has been an unsolved problem in physics for quite some time now. And what actually is this problem is that standard theories like the quantum theory, general relativity, if you use those arguments from the theories, they predict that there should be zero asymmetry, which means there should be the same amount of matter as there is antimatter in the universe. While the observations show a very large asymmetry. Practically, we observe mostly matter in the universe and practically almost zero antimatter. So now to explain this asymmetry, we have to satisfy the so-called Sakarov conditions, which are the Barium number has to be violated, C and CP symmetries have to be violated, and the interactions have to deviate from thermal equilibrium. So if we satisfy all these three conditions, we can explain the Barium asymmetry in the early universe. In the universe observed, but it has been frozen in the early universe. So our mechanism, how we did that, we used the holographic principle and the thermodynamics of horizons, and then used the GUP or generalized uncertainty principle to modify the horizon, and thus rederiving the Friedman equations and satisfying the Sakarov conditions. At least the last one, the deviation, but the first two are satisfied with a CPT violating term, which stems from supergravity, which I will go into detail later. And this work is based on the paper that has been today published in Archive. And you can also go check the paper. So the quantum gravity problem is that we have two successful theories. We have a quantum theory on one hand, and we have the gravitational general relativity on the other hand. And there is no nice way to combine these two theories. And that's why we need a theory of quantum gravity, but there are no proofs nor nothing to prove quantum gravity theories or approaches, but we have a great intuition of what quantum gravity may imply. And one of such things is the minimal length. And a nice way to incorporate minimal length is to modify the Heisenberg uncertainty principle, where here in the black script is the usual Heisenberg uncertainty, while we have those two terms in red, and those two terms are due to minimal length, and should explain quantum gravity phenomenology. So here we have parameters alpha and beta, which are called the GUP parameters, and are expressed as seen here, where alpha naught and beta naught are dimensionless parameters. LP is the Planck length, and H bar is the Planck constant. And of course, alpha and beta are called the linear and quadratic GUP corrections. So this model, this phenomenological model, describes any length scale, alpha naught LP and square root of beta naught LP, between the electroweak and Planck scales. Since we know we have not observed any quantum gravity effects down to the Planck to the electroweak scale, but the Planck scale is believed to be the smallest one. So the quantum gravity scale should be anywhere between that, and this model, the GUP model, explains that it for any length scale. It doesn't have to be the Planck scale itself. So how do we then use this? We apply the GUP. I will refer to the generalized uncertainty principle as GUP from now on to abbreviate it. And we apply it to quantum mechanical and gravitational systems. And then we predict deviations from standard theory. We assume that there should be some and that experiments can detect them, or we can provide explanations for unexplained phenomena. as in this case is the Barium asymmetry that we observe in the universe. So let's continue to the modification of the Bekenstein-Hawking entropy. We can write the GUP in this usual form. Before I showed you that the previous form was in the commutator form, but it can be written in this usual form. And we also consider a change of the area of the apparent horizon, where we use this holographic principle, where we can write our d-dimensional theory. If you have a d-dimensional volume, we can write this theory in a d-1 dimensional theory, as on its surface. So we will now consider the changes in the area of the apparent horizon of our apparent cosmic horizon. So this change in area is if a particle with energy E gets absorbed in our cosmic horizon. Then this is the change in the area of our cosmic horizon. And LP is, of course, the Planck length, and delta X is the uncertainty in position. So when we solve the quadratic equation from this GUP version, we solve for delta P, and we get this expression. So this is then also proportional to the energy of the particle, and this is then the energy that goes in this equation. Pardon me. Then the position uncertainty is then the whole diameter of the observable universe, the horizon. So if we square that, we get the delta X squared is the area divided by pi, the area of the apparent horizon divided by pi. So then we plug these equations in, and then we go to consider the entropy. We will use this result in the next slide, so just try to remember this delta A. So the Bekenstein-Hawking entropy, as you know, is written as the area. It was first introduced for a black hole, but the holographic principle suggests that this can also hold for any horizon. So we have a cosmic horizon with area A divided by 4 times Planck length squared. And if we have some modification of the uncertainty principle, or we want to modify this entropy in any way, the only variable in this equation is the area. So if we modify it, the area that is not just A anymore, but it's something, a function of area. And then a useful quantity here is then to introduce the derivative of this S, as you shall see in the following slides Y. So when we differentiate the Hawking entropy by A, we get this expression where F prime is just this function derived over the area. So then using the minimal change in entropy, which is delta S min, which equals logarithm of 2 in natural units, and then divided by that delta A that I showed you on the previous slide. And this logarithm gets then absorbed in a normalization constant, which gives us 2 pi, and then gets absorbed in this beta star, which I'll show you later what it is. So this is the form we get. And then if we want to read out what this F prime of A is, we just compare these two equations to each other, and we get this function of A. And here alpha prime and beta prime, alpha star and beta star are just redefined quantities for ease of use. And to obtain the modified Bekenstein-Hawking entropy, we just have to integrate this. I know this function looks pretty tedious to compute, but it actually has a exact solution in a closed form. So now just don't try to remember this, but we have this function which we will use later. This is just setting the stage for the explanation. Now we will go to modify the Friedman equations using this modified Bekenstein-Hawking entropy. So what are Friedman equations? Most of you know they are the equations describing the dynamics of an expanding universe, which can be derived in 2 ways. The most rigorous way is, of course, using general relativity, but the holographic principle actually allows these equations to be derived from the thermodynamics of horizons. And we shall, of course, consider the latter case. So we consider a first law of thermodynamics, which we all know and love in this form. And I'll explain these quantities. In short, so this energy here, this is the total energy in the volume of the observable universe. Then this is the Hawking temperature, which of course, as I stated before, regarding the holographic principle, it can be also used for any horizon, not just a black hole. And then this entropy, we write it here for now in this general form with this function f of a. And the work density is just a trace of the projection of this energy momentum tensor. And the volume, of course, for an n-dimensional theory, we can write it in n dimensions, is given here, where this omega n is just the volume element for an n-dimensional sphere. So what do we have to do here? We have to differentiate the energy, we have to differentiate the entropy, and we have to differentiate the volume. And of course, write it everything in terms of dA, like in area. And then we plug everything, all those things in the first law of thermodynamics. And then we can derive the first Friedman equation with that, where we see that this f prime a gets its place here in this part. So then we use the continuity equation, which stems from the energy conservation law. We plug it into this equation, integrate it, and we then get the second Friedman equation, the second modified Friedman equation. So as in the usual theory, where f prime of a is just 1, we plug this in, we obtain the usual Friedman equations as we expect. But that's not interesting for our case, and we want to use that function that I showed you earlier, that f prime of a, and we plug it in here, and we plug it in here, and we compute this very tedious integral, which very interestingly has an exact form, exact solution. You don't have to do any Taylor expansions or approximations to compute this integral. However, I had to shorten the notation, so I had to expand it in a Taylor series just to present these two modified Friedman equations, of course, in 3 spatial dimensions. This n refers to spatial dimensions, not space-time. Because if I would write just this first Friedman equation in an exact form, this whole page will not be enough. It's very long. It has a very long solution. But if we expand it just to first orders in alpha and beta, this is what the modified Friedman equations using the generalized uncertainty principle look like. Now let's go to explaining the actual Barium asymmetry using what we have seen so far. So some theories of supergravity have this extra term in the action, which violates the CPT symmetry. And here you can see this J mu is the baryon current, and which is coupled with the derivative of the curvature. This is the Ricci scalar. And here m star, this is just a cutoff scale of this effective theory. So of course we consider the GUT, this means the grand unified theory interactions, which in themselves violate the baryon number, and also use this term, which violates C and CP symmetries. So in this case, now we already satisfied 2 Sakarov conditions. Now we have to just satisfy the last one to produce the Barium asymmetry. So we can then read the chemical potential from this CPT violating term, which is because only the time derivative part survives of this part. So this is a chemical potential for baryons and this for antibaryons. They just have a different sign. And then the useful quantities, which will be evident how they are useful in the next equation, are the number density, baryon number density, and the entropy density. And they're useful because they're used to define this baryon asymmetry parameter eta. And one interesting thing, you that already studied this, you know that there's this factor of 7, because eta is defined as the ratio of the number density of baryons divided by the number density of photons. So the number density of photons and the entropy density have this relation of the factor of 7 between them. So this is why we use this here. And then we plug all this in, we plug this chemical potential in the baryon number density, and then divide this by this entropy density to get this expression at the end, which is evaluated at some decoupling temperature. And this decoupling temperature is the temperature where the baryon violating interactions freeze out when they go out of equilibrium, and the baryon number is after this temperature is conserved, but before that is not. So we have to consider this one. So now how to proceed, how to actually use the Friedman equations. We write the energy density and pressure as the equilibrium values plus some small variations to them. So we know if there is no variations, we have thermal equilibrium, we have no baryon asymmetry production. So we have to have some small variations to deviate from the thermal equilibrium. And how to get them? We plug this, these two into the Friedman equations, and then just express delta rho and delta p in terms of these GUP parameters. And of course, we use the equation of state with this W, so this can be written in this form in general. So we see if there is no GUP, this means alpha and beta parameters, or in this case, alpha star and beta star are 0, we get no perturbations in or variations in the energy density and pressure. And then we compute the time derivative of the Ricci scalar. Of course, Ricci scalar is just the trace of the Einstein equations. We plug this delta rho and delta p in these equations, and then we plug all of this in here and derive it. Make a derivative and evaluate it at W being equal to 1/3, because 1/3 corresponds to the radiation dominated era where the radiation pressure dominates. And this is the case because this is in a very early universe before the baryon violating interactions froze out. And we can see that this derivative of the Ricci scalar would also be 0 if there would be no GUP corrections, because we have in any term we have these alpha and beta parameters. So now we have to just express this equilibrium number density. We express it for the relativistic particles, where this G star is the number of degrees of freedom of all relativistic particles. And we plug all this in that equation for the baryon asymmetry, and we get this expression. And this expression here, we see that GB, of course, I forgot, these are the number of degrees of freedom for baryons, and G star is the number of degrees of freedom of all relativistic standard model particles that contribute to the entropy of the universe. So now what we see, okay, these are just some numerical factors. When we plug in the number, this is a numerical factor and this is a numerical factor. And then they are dependent just on alpha naught and beta naught parameters, which are the GUP parameters. Of course, if they are 0, we have no asymmetry. So, but if we have quantum gravity effects, if we have a minimal length scale, this baryon asymmetry becomes 0. So the minimal length actually produces this asymmetry in a way.
I'm sorry, you have a couple of minutes left.
Okay, I'll wrap it up in a minute or two. So we plug in this TD with the decoupling temperature is thought to be this MI, which is the upper bound to the tensor mode fluctuations in the inflationary scale. And we use this M star as the reduced Planck constant to plug these values in. And now to compare this to the experimental bounds, which were observed, which are between these two values, we then can constrain the GUP parameters to their values. I will not discuss the numbers in detail, but we have considered a linear GUP model where we set beta to 0, on the quadratic model where we set alpha naught to 0, and the linear plus quadratic where they are related, and the linear plus quadratic where they are unrelated, the GUP parameters. And to conclude the talk, the work that we have done is in a way a test of fundamental physics of nature, how this fundamental physics can affect a grand scheme like the baryon asymmetry, a big problem in nature. And this mechanism that we propose satisfies all Sakarov conditions. And the interesting thing is also that the GUP modifies the apparent horizon area, and in turn the Friedman equations, which can also be used more broadly also in cosmology. And the things we have found that, as I mentioned already before, that the results suggest that quantum gravity effects could have been the cause for generating the observed baryon asymmetry. And also this work does not constrain the parameters to some upper bound because we didn't detect anything, but we did detect. So this sets the quantum gravity length scale to these values, 1.3 times 10 to the minus 31 meters and 4.76 to the 10 to the minus 31 meters, giving these conditions. These numbers have been derived from the numbers on the previous slide. Also, one thing we noticed that the quadratic GOP parameter turns out to be negative, but after some thought has been put into this, it also suggests that this also suggests a minimal length. It doesn't violate anything that we impose. So that was all from my side, and thank you very much for your attention.
Yes, thank you very much for a nice talk. We have a few minutes for questions. Please raise your hand if you want to ask some question. Yes, Jan Krapisz, please.
Hi, thank you for a nice talk. Actually, I have a question. When you consider this bound on alpha 0 and beta 0, can't you turn it other way around in a sense? Can you use, I don't know, to put some values of alpha 0 and beta 0, I don't know, such that this intermediate scale is the Planck scale, for example, and then bound the number of species that you should have. So in a sense, by this by the principle that you do, you will bound the content of various particle physics theories. Is that possible?
I think so, yeah. If we look at this equation, yeah, then if the number of degrees of freedom are different, but it will not change much because that's still in the order of 10 to the power of 2, maybe, because this is G star is around 106, I think. So if we constrain it, like there would not be much difference. So these alpha and beta parameters technically should have values in this ballpark. In a way, I hope this answers.
Could you rule out some theory, or I know, put a favor for some theory?
Maybe yeah, with a more detailed models, that could be possible. Yes, to rule out some theories. That would be possible, definitely. Yes.
Okay, thank you.
Okay, thank you. Are there any other questions? We have time just for one short question, if there is any. Okay, I don't see any more questions. Thank you then. And our next speaker is Jan Krapisz, actually a person who actually asked the question. So you can continue with your presentation. Please try to share a screen, and if possible, you can actually, yes, show yourself. Yes. Hello.
Just a moment. There is my. Okay, there is my presentation. I hope you all can see it.
Yes, we can see. It works fine.
Okay, great. So may I start? All right, I guess the silence means yes. Okay, so hi everyone.
Excuse me, let me check. Just please let me check the time, but I think, well, we have just 1 minute, so I think you can start.
Okay, great. So hi everyone, my name is Jan Krapisz. I'm a PhD student at the University of Warsaw, and I would like to talk about this, about quantum gravity and grand unification. This is a work in progress, but we have some interesting preliminary results with Aaron Held and Lohan Sartore. And so, yeah. Let me just move you because I cannot see my slides. Okay, so as you know, standard model of particle physics works so far surprisingly well in the LHC. Before LHC, there were many claims that supersymmetry would be found or other new particles would be found, but it works surprisingly well. As you know, it's based on this SU3 cross U1 cross SU2 cross U1 symmetry. It has a Higgs boson and it has this 19 free parameters. However, on the other hand, we know that some model has to be extended from particle physics point of view, both from, let me say, theory arguments and observational arguments such as dark matter or Barium Asymmetry, which has been mentioned previously. So one of the most popular way to do is grand unification, which is a nice framework to explain the structure of standard model, explains its parameter space, and provide possible candidates for dark matter or neutrino masses mechanism, Barium symmetry, etc., etc. So in a sense, grand unification 101, how it works. So we have the renormalization group equations that change the couplings over the scale, and there should be a certain scale at which all the free couplings unify, where they join into one coupling of a larger gauge group. This provides a really nice and symmetric picture in higher energies. And on the other hand, let me remind you that actually, this grand unification theories, they often predict or almost always predict proton decay. And let me remind you that actually proton decay is the highest energy observable that we have. So possibly with that observable, we could in a certain years even probe quantum gravity scale. So it's quite appealing from the phenomenological point of view to study it. However, grand unification theories also have its dark side, since the simplest SU5 grand unification didn't work out because there's no one scale unification. So you have to build a far bigger model like SO10 or E6, and put a plethora of scalar particles and scalar fields in order to break this down to the standard model. And furthermore, the Yukawa and gauge couplings in such large models are constrained experimentally, while the quartic couplings and the masses of the scalar are not, which means that starting from any various quartic, that the parameter space that we have to study those models is really enormous, and it means that many different breakings could be possible, which makes these models very unpredictable. On the other hand, let me take this point of view on quantum gravity, that quantum gravity should also explain these questions that we pose on the matter side. So for example, why the values of the couplings are such that as they are. This is the case, for example, for string theory or asymptotic safety approaches. So the question that we have asked together with my colleagues is, how big is the set of possible quartic couplings that can be set by quantum gravity realizing viable phenomenology? What does it actually mean? It means that we do not take any particular quantum gravity model. We just set the couplings, these quartic couplings, to take arbitrary values at Planck scale, presumably set by some quantum gravity mechanism. We don't know what that mechanism is, but it's enough that we put them. Below below that scale, we assume that there is grand unification, and below that, there is standard model. And we wanted to study this to see how vast this parameter space with viable phenomenology is. So let me be more specific. So first of all, we assume that the grand unification has to hold, so that the breaking of the grand unified group has to take place at scales that are high enough where they actually take place. So it's roughly up to 10 to the 14 GeV, which is quite, let me say, quite relaxed bound. Furthermore, since there's no one stage breaking, so there's no breaking like SU5 to U1. So out of one big gauge group, we get standard model couplings. This is not allowed. So we do not allow for such situation to happen. Furthermore, we consider the proton decay bounds, which is that once I break towards SU5, the final breaking in that direction has to be beyond 10 to the 15. Again, it's quite relaxed bound. And finally, in the grand unified community, one says that there are various minimas, but one breaks towards the deepest one. So one has to require that the standard model to be the deepest minima. Let me say that these conditions are very minimalistic and very quite relaxed. One could also put leptogenesis, neutrino generations, CP violation. I don't know what else, and many other phenomenological constraints. But even with this relaxed one can severely restrict the parameter space. So let me now introduce the model that we are discussing. This is the model based on the famous SO10 unification with fermions in the 16 representation, such that all of the standard model fermions joined into the 16. And the scalar part is 10 plus 45 plus 16, which is quite minimalistic model. And actually it has a non-viable Yukawa sector. However, we picked that one for, first of all, for some simplicity, because the minimalistic one with realistic Yukawa sector has twice as much scalar couplings. But this scalar couplings actually turns out to be not very relevant for the analysis that we have performed. So this is why we picked this simpler version. Furthermore, we chose to work with a model that is classically conformal invariant, which means that the masses are generated via Coleman-Weinberg breaking. This is first of all due to the fact that such a construction allows for no quadratic divergences, as it has been shown in the literature. And secondly, due to the fact that even if one would like to study these models with masses, the radiative minimas that we have found in our work will be still there. Furthermore, this 45 appears in vast studies of Calabi-Yau compactifications of string theory, and is not coupled to Yukawas, which would prove crucial for our analysis. In particular, this means that these couplings will always turn negative along their RG flows, and depending on the value at the Planck scale, they will do it faster or slower, but they will always do so because there's nothing to counterbalance its flow. Furthermore, this model has a in principle viable model breaking direction. And it's particularly interesting, was particularly interesting for us because this model has been studied in the 80s, and there was a general consensus that it's that the model with 45 scalar field are not viable. However, the recent papers show that the non-SU5 vacua are possible after quantum corrections. I will, in this talk, I will a little challenge that claim, since not all of possible vacua has been taken into account in the study that revived that model. It has four maximal subalgebras, which are SU5 to Patti-Salam times, so SU4 times SU2 times U1, and SU3 times SU2 times U1 times U1. And SO8 times U1, which is not towards standard model. And this final maximal subalgebra will be crucial for our studies. So let me show you how many of these breaking chains are in this SO10 models. We have this road that goes through SU5 or SU5 cross U1. And we have the road that goes through the Patti-Salam type models. There's a lot of those, a lot of VEFs, a lot of breaking chains. So in principle, this is why this hasn't been studied, because there were no methods to do this. However, Lohan and his supervisor, they developed this fantastic code, Pirate, which enables to calculate the beta functions for such large models. And furthermore, with some enhancements, it allows to do the resummation of effective potential, which hasn't been done before. Let me only show that these beta functions are quite complex. This is the example for just the SU5 type model, but for the SO10, these are far more complex. In particular, we have 10 scalar couplings with all the possible interactions. However, having those beta functions, we can put arbitrary values at the Planck scale and just study what happens below, and then do the resummation of effective potential to find the corresponding Coleman-Weinberg minimas. Let me tell you about the preliminary findings that we have. First of all, among these maximal subalgebras like SU5 cross U1, SO10 cross U, SO8 cross U1, and the Patti-Salam ones, the Patti-Salam is disfavored. What does it mean? Actually, it means that one would like the model to break towards Patti-Salam, because then it's easy to perform the grand unification. However, going through SU5 cross U1, U1 requires large threshold corrections, or that is even impossible if you go through just through SU5 if 16 breaks as first. Secondly, the two-step breakings at once are favored, which are again against the grand unification. So it seems that the model is either non-viable or require large threshold corrections. But however, let me stress that these are preliminary findings of our work, and this is in a sense still work in progress, but after a couple of months analysis, we are very convinced to that, but let me stress that once again. So as I have said before, there are more constraints that can be taken into account, such as leptogenesis, neutrino masses, dark matter constraints, etc., that could tighten this already tight model even more. Let me show you what we get actually. So this is the study beyond the maximal subalgebras. This is the counting of the deepest minimas over 10,000 sample. So for example, one can see that SO8 times U1, so the non-standard model vacua is quite dominant. Also the breaking toward of SU5 towards non-viable SU4 cross U1 is quite dominant. Also direct breakings towards standard model are quite are possible, and the breaking towards SU5 already, which is against the grand unification. And the the Patti-Salam models are actually not even here because we haven't identified them as the deepest minima anywhere in the parameter space. There is the parameter space. So these are the 45 couplings. These are the 16 couplings, and these are the portal between those two. And one can see nicely that there are various regions in this, and actually that the dominant over these regions are SO8 and SU5 triggered by 16. This comes from the fact that the 16 has a very sharp running, and it has to be really, really big in order to not be the first to break the SO10 vacuum. So in a sense, we find a large hierarchy over these couplings in order to get, for example, this other than this breaking. So finally, let me connect to some known quantum gravity theories, both asymptotic safety and string theory. In both, the scalar couplings are predictions. In asymptotic safety, the values of the couplings stem from their fixed point values and critical exponents calculated at these fixed point values, which famously there's this Higgs mass prediction made by Shaposhnikov and Wetterich in this approach. And as it turns out, there is no stable non-trivial fixed point potential for the studied model within the quartic coupling truncation, which would mean that the model will break far beyond Planck scale, whatever that means, which could mean that the grand unification cannot occur in that kind of settings. While in the heterotic string theories, the quartic couplings are tied to the gauge coupling of the string gauge group. So like when you have SO32 times SO32, then the couplings would be tied to the values of those couplings. And it seems that this hierarchy produced by string theory would be really interesting to study whether this would be in line or not in line with the hierarchy that we have observed, and what are the possible breakings of such string theory models. With that, let me thank you for your attention. I guess I'm early on time, so I would happily take some questions.
Thank you very much. You're actually almost exactly on time. Thank you. And we have some time for questions. Please raise your hand if you want to ask a question. Well, I don't see any question. We can wait just for a second or two.
Okay.
All right. So there are no questions. Then thank you very much for your talk. And as a result, we have now 6 minutes break. And because I really would like to start the next talk exactly on time, because there might be some people switching on and off from another sessions. So let us meet exactly at 10:50 Central European time.
Okay.
Which is 5 minutes from now. Okay, hello again. I hope everybody had chance to get some coffee or tea or something to drink, or grab a snack or something. And we now turning to our next speaker, which is Samuel Barroso Belido. It is, yeah, hello, hi Samuel. Okay, please try to share your screen, and as usual, we'll have 20 minutes plus 5 minutes question time. So you can go ahead. Thank you. You need to switch off your switch on your microphone because you're muted at this moment. I cannot hear you.
Now, okay.
Now, yes. Okay, go ahead.
Thank you. Let's see how I go back to the sharing. Now, okay. So
we see your screen, we hear you, so you can just.
Okay. I'm Samuel Barroso Bellido from Spain, and I'm doing my PhD in Poland in the University of Szczecin. And this talk, this entanglement entropy at critical points in the multiverse, gave rise to these two articles with Adam Balsashak, Mariusz Dabrowski, and Salvador Robles Perez. This at the beginning of this year, and now I'm publishing another one, but it is to be published. So I'm going to talk about entanglement entropy in the multiverse. And the scenario I'm going to present is quite simple. It's a pair of universes which bond together, so they are entangled from nothing. We will arrive how we get to this scenario. The questions we are going to try to solve are these ones. How do we find entanglement entropy of the pair? Calculating it. If this is high at the birth or not, which we expect that this is high. And if this is high at the critical points of the classical evolution, where the maxima of expansion and the minima of expansion or any other kind of critical points. This question, we had this question because of the Kiefer article in 1988, the wave particles in the mini superspace, a well-known article in canonical quantum gravity. And this, he stated that at the maximum of expansion of the universe, quantumness of the universe that is not trivial. So we would like to answer to this question. The topic is quite simple, and the outline is to remember you some canonical quantum gravity, if there are someone who is not familiar with it, and present you what is the third quantization in canonical quantum gravity, which is not the same that in string theory, and what is the invariant representation, and how we calculate and what are the results of entanglement entropy, and then some conclusions and perspective of the theory. First, let's remember you what is the canonical quantum gravity. Canonical quantum gravity in the 50s, there were the first description of the Hamiltonian formulation of general relativity and the IBM formalism. The IBM formalism and this Hamiltonian formulation gave rise to this canonical quantum gravity by De Witt and Wheeler. The theory, this canonical quantum gravity, is just to replace in the Hamiltonian description the metric by the 3 metric and the lapse and the shift function, which is this notion of find a hypersurface and parameterize the hypersurface of this 3 metric to get what is let's say, to parameterize the hypersurface in such a way that the time plays a role of how the hypersurface changes, the 3 metrics change. In this sense, on the IBM formalism, you find this Wheeler-De Witt equation, which do not contain the notion of time. It doesn't contain the notion of time, and this is important. And the momentum is replaced by the partial derivative of the metric. This is a well-known theory. This Wheeler-De Witt equation has only two things here, which is the wave function of the universe that contains, that it is the description of everything which is contained into the universe, and the Hamiltonian. This Hamiltonian is dependent on your model, your desired model. So each model has a different Hamiltonian. The problem with this theory, this super space, is that it contains, in reality, infinite degrees of freedom. So for us to study something simple, which is solvable, we reduce the scenario to the mini superspace. So we choose, for example, Friedman-Lemaitre-Robertson-Walker universe, where everything is homogeneous and isotropic. So the degrees of freedom of gravity is given by the scale factor, which is a function of time, just depending on time. And as many matter fields we want to include in the theory. For example, for a massless scalar field, the potential is 0, let's say, and then the Will-David equation looks something like this, where we use this parametrization of the scale factor A. This alpha is now our time variable. So we have something like this, where we quantize the scalar field like this. Okay, this psi square is this partial derivative. And we see that this Hamiltonian here is separable. We have the part which is only depending on alpha, on the scale factor, and the other which is only depending on the scalar field. So these two functions give us this, the Hamiltonian of the scalar field give this eigenvalue. This eigenvalue can be included here in this Hamiltonian to change this function as a function of everything we had at the beginning, the curvature of the universe, the cosmological constant, the scale factor, whatever, and the energy of the scalar field. So this equation now, the Will-David equation for massless scalar fields, become a harmonic oscillator-like differential equation. And this is important for our study because this is something we need. The third quantization in canonical quantum gravity is something to be introduced, which is known, there could be someone not familiar with this third quantization. Remember that we, in quantum mechanics, change the notion of particles of this wave function to the notion of a wave function, which is an operator over vectors of the Fock space. So we define what is the annihilation and creation operators and what is the Fock space, which is the vibrations over the fields, etc., usual quantum field theory. And this Fock space is an infinite Hilbert space, but countable. Exactly the same, we can do this for canonical quantum gravity. We can promote our wave function of the universe, our only and beloved universe, to some operator over fields of universes. This Fock space is now an infinite space, Hilbert space, and you can create like an anti-universe and a universe that are created from nothing, or a pair of universes that simply decay in a son or a doctor universes. Some scenarios like this, and you can imagine the rest of the diagrams. But we face a problem. We face the problem, which is usual in quantum field theory in curved spacetime. When you apply quantum field theory in curved spacetime, you are not using anymore the Minkowski background, but any other generic background. You use a metric, and this metric, when you introduce this, the vectors of the Fock space are not constant. So in general, so the expectation value of the number of particles you have in your system, for example, the vacuum, is not constant along the evolution of the expansion of the universe, for example. So the number of particles is not well defined. It's something which is not well defined in quantum field theory in curved spacetime. So this is exactly the same that happens in our theory, because we don't have a static background, or we don't have a Minkowski spacetime. We have a generic spacetime. And the solutions to this problem of the ill definition of the particles are usually using adiabatic expansion of the theory, expecting that the expansion of the universe is smooth, etc., etc. And adiabatic order, the definition of particles is well defined. So we renormalize the theory and everything is okay. But that yields many problems. And the invariant representation, which is what I'm going to introduce in the next slide, which gives you a way to have invariant vectors, and the vacuum is always constant, so the number of universes is always constant. You can find an invariant operator n such that the number of universes is constant. So there is a representation for which n, the operator n, the number operator, is constant. So the number of universes remains constant. For these third quantized universes, this notion of not having a constant number of universes is something unnatural, because we measure everything from the beginning of the universe and we do not feel any change or nothing. We see our universe to be the same. If something like this is happening, is very unlikely. So the number of universe for us, we suppose that it is very natural to imagine that the number of universes of the multiverse is constant. In this scenario of two universes, there will be always two universes, not in. So we are going to use this invariant representation for our formalism from now on. This invariant representation, if you use this notation in this scenario where you have an anti-universe and a universe, and the vacuum is this point in the space-time where there is no space and no time, the notation we use is this one. It's a vector for the anti-universe and the universe. This bipartite system is notated like this. And in 1969, Lewis and Riesenfeld, they developed in an article the invariant representation for time-dependent harmonic oscillator, which is exactly what we had. In our Will-David equation is a quantum harmonic oscillator, which is time-dependent. And in that case, we can describe the vectors of the invariant representation in terms of the diagonal representation. This is an infinite sum, and this is something which is important because this solves most of the questions when I give talks, this talk, and because no one see that rapidly. And then how we calculate entanglement entropy using these invariant vectors? Easy, because the density matrix then is just this, and the vectors are defined from the formalism of Lewis and Riesenfeld. So we find the density matrix, and we trace out the degrees of freedom of one of the universes, which is just tracing out this U minus, for example, and we get the density matrix of one of the universes. So for this bipartite system, the entanglement entropy is defined like the von Neumann entropy in general. There are many other ways to find the entropy, but I will talk about this later. So we use this formalism to find entanglement entropy of the universes. We found, for example, in a two-dimensional system, this is a scalar field as the only gravity degrees, the only degrees of freedom by gravity, and the scalar field for a closed universe k equals 1, where we set the system to have a maximum of the expansion of a classical expansion in A equals 1. This is A, exactly. So this blue surface is the entanglement entropy. And you can see that at the beginning of the universe, when A is equal to 0, the entanglement entropy is constant. And exactly at the maximum point of the evolution is infinite. In this scenario, this is the most general scenario we found, but the system, this psi is massless. The potential is 0. In this scenario, this is quite subtle. We don't have a reason why at the beginning the entanglement entropy is not going to infinite, but it is only in this model, when psi is massless, that we find that the entanglement entropy is finite. Indeed, the temperature of entanglement, which is over measurement of entanglement that is usually used, is constant, not, but is finite along the evolution at any point of the evolution of the universe. And this is something strange. But for example, for a massive scalar field with this potential, we need to change variables in the Will-David equation to find a way to find invariant representation. But well, the calculations are done, and you find that the entanglement entropy at the beginning is infinite, but this doesn't contain any critical points. So we didn't study this. But for example, I wanted to show you that for a massive scalar field or any other models, the entanglement entropy is at the beginning infinite or finite and decreasing. So at the beginning, the entanglement entropy is high, and then it decreases. And when a maximum is when it approaches a maximum, it increases again. So at the maximum or minima, the maximum at least, the entanglement entropy is infinite, and at the beginning it is high. So we found those values of the entanglement entropy. And in this case, we find an entanglement entropy is infinite at the beginning. And it is strange, no, it's like wavy behavior along the evolution of the universe. For example, we asked ourselves a question, which is what happened at the minima of the evolution. We used this model of Dabrowski, Marius Dabrowski, with a classical field phi. We only take the degrees of freedom phi dot and phi in the Hamiltonian, writing it like the density and then in the barotropic parameter using this usual equation of state for the scalar field. And we arrive to a model which is just a sinus. So it contains a minimum, in the expansion of evolution. So at this minimum, we find using these parameters, with using wall-like matters and string-like matter and a negative cosmological constant, a closed universe, we find that there are a minimum and the entanglement entropy also diverges at the minimum. So we found that the entanglement entropy is infinite at any critical point where h, the Hubble parameter, is 0. For example, in this inflection point here in the middle, the entanglement entropy is finite. So it is interesting to note that this entanglement entropy, which is somehow a measurement of the quantumness of the system, is infinite at the critical points, but not always at the beginning of the universe. This is something to be studied later, but the conclusions are interesting. And we ask ourselves, what is the shape of this entanglement entropy around those critical points? We expect a function of the entanglement entropy, or depending on this Hubble parameter, where h is approximately 0. So we found, using a model where this wave function of psi and the scale factor is like this, Fourier transform, where the modes are just the modes distribution is just a Dirac delta. So there is only one scalar field, like A equals to I phi. So in this simplest model, which is the simplest model, in this model, we found that the entanglement entropy analytically is like minus the analytically, and with this for other models, like using a fitting of the function, we found that the entanglement entropy is exactly minus the Shannon information. We expect something like 1 over h squared, but we found that this is approximately like minus the Shannon information. So we don't know why. We don't have any reason why, but we found this with perfect accuracy, almost perfect accuracy. So for example, furthermore, we found other measurements of entanglement entropy. We found Sally's entropy, we found Renyi entropy, and all of them had the same behavior. They are completely equivalent exactly at any model we studied, and we studied many models. So they are equivalent, and this is nice. The temperature of entanglement, which is defined like this, where this R is calculated using the Bugolov coefficients of the transformation from the invariant and the diagonal representations, is also a measurement of the quantumness, as I said, and this is found not to be a good measurement of the quantumness of the system in 2 or 3 models we studied.
Excuse me, you have a couple of minutes left, so please conclude.
Perfect. This way of measurement is not good in our models, so we will say that this is not a way to calculate the measurement, the quantumness of a system. So, and sometimes the entanglement, for example, sometimes the entanglement entropy goes to infinite when the temperature is not going to infinite, and it decreases or goes to 0. So this is important because sometimes we have seen in some articles that the temperature of entanglement is used as a measurement of a quantumness, and that is something subtle and must be one should take it with care. And conclusion. So we found a way to calculate the exact entropy of entanglement of a pair or any other scenario. We find that at the beginning, the initial singularity is high, infinite when phi is classical or when phi is massive, but finite when phi is quantum and massless. I forgot to put this here. At the critical point, we found that the entanglement entropy is always infinite, confirming Kiefer's hypothesis that at the maximum expansion, the quantum energy is infinite or high. And we found the relation like the Shannon entropy. This is minus the logarithm of h around the maxima and minima of the evolution of the classical universe. Some other measurement of entanglement seems not to be as good as we expect. And the perspective of this theory is to study this entanglement in a more realistic scenario, full quantum field theory of the universes, and etc. And we are in research of the imprints of on the CMB of this pair scenario using the entanglement entropy and see how the Friedman equations are changed due to this entanglement. So these are the references if you wanted to check something. And thank you very much. That's all.
Thank you for your talk. We have a couple of minutes, 4 minutes for questions. Please raise your hand if you want to ask a question. Jan Novak, please.
Hi. Please, could you repeat the argument why the number of universes is constant? I mean, what was your argument? I mean,
the argument is that our universe is not changing along the evolution of. I mean, this is quite subtle because in quantum field theory we are treating with particles that are just particles. There is nothing inside. If we imagine that our universe is like a particle. I don't know, but I expect, I mean, the most natural way of thinking is that I expect that if there is a changing number of particles with interactions, I mean, our universe is having interaction with other universes or something to change the number of universes, we should notice something inside the universe. And we notice that our universe is not changing inside in topologically or something in general. So we expect that the number of universes is constant because we see our universe to be the same as always. This could sound like an anthropological reason, but it could be something like that. There are more reasons I can not remember now, but there are more. I thought that this is the most natural way of thinking about this.
Thank you.
Okay, any further question? Well, if there are no further questions, thank you very much once again. Thank you. And our next speaker is Abdel Nasser Tawfik, and I'm not sure he's with us. So let's try to wait for him for a couple of minutes. He actually contacted me yesterday trying to reschedule his talk, but it was already impossible. So perhaps he actually wouldn't join us at all. So let us wait for this for a few minutes, and if he's not here, we'll just take a break so that the next talk, the talk after his, is going to be on time. Okay, so apparently Dr. Tafik is not with us at the session, which means that we can just take a 25 minutes long break, and we meet again at 11:40 sharp for the talk of Giulia Maniccia. Okay, thank you, and let's meet in 25 minutes. Okay, hello everyone again. We now turn to this next speaker, Giulia Maniccia. If I spell your name correctly, please share your screen.
Yes, it is correct. Thank you.
Okay, you can share your screen.
I
and
will
we can
start
now.
sharing. Can you see the presentation?
Yes. Yeah, well, that works fine.
Okay, perfect. And just
and as usual, you have 15 minutes. Sorry. Let me just check the schedule because I might be mistaken. No, you have 20 minutes plus five minutes question time.
okay, thank you. Can I start?
Yes, please start.
Okay. Good morning, everyone. And first of all, thank you for this opportunity. I am Giulia Maniccia, a PhD student from Sapienza University of Rome. And today I will talk about a recent proposal regarding the non-unitarity problem in quantum gravity corrections to quantum field theory with a Born-Oppenheimer approximation, which was the content of a recently published article. So first of all, I will start describing briefly the problem of time and the WKB expansion of the gravity matter system. Then I will expose our proposal for the non-unitarity problem. Then I will briefly talk about possible applications in cosmology. And finally, the relation of our model with a reference frame fixing procedure, which gives us an incoherent task. So first of all, let's start with the first point. As was briefly but nicely stated in the previous presentation, we can use the canonical quantization approach to gravity by using the Arnold-Desser-Misner formalism, which consists of foliating spacetime into three-dimensional spatial hypersurfaces and the normal direction. It is seen from the Hamiltonian formalism of gravity that the universe wave function depends on the equivalence class of three geometries Hij, which are induced on the hypersurfaces, and obviously on the matter fields. Then the dynamics of the system is described by the Wheeler-DeWitt equation, where we have the gravitational terms and the matter terms. It is known that this equation is equal to 0. So this gives us a problem because if we apply the canonical quantization scheme, we see that the wave function does not depend on time, so it has no evolution. And this means that we must use a relational time to describe the system. A way to do this is with the Wenzel-Gramme-Brillouin expansion, which is a method where we write the wave function as an exponential, and the action, which is in the exponential, is expanded perturbatively in some parameter k. Then each of these terms is decomposed into a part for the semi-classical background and a part for the quantum subsystem, which can also depend on the semi-classical part. This can be applied to the Wheeler-DeWitt equation, which I have written here in a more compact form. So we can identify a semi-classical background with the gravitational part and use this semi-classical background to define the time evolution for the quantum subsystem. However, the main problem is what is the dynamics that emerges from this expansion. The first work that applied this procedure was the work by Vilenkin, we choose an expansion in the Planck constant and computed the model only up to order h bar. In this way, the author recovered the Schrödinger equation for the matter fields with a suitable definition of a time parameter. However, we have shown that if we expand this model to the next order, we find an equation for the matter fields which has non-unitary terms. Another core work was the work by Kiefer and Singh, which performed an expansion in a constant m, which is proportional to the square of the Planck mass. And the computation was done up to order 1 over m. In this way, the corrections due to the quantum gravity to the matter dynamics were observed, but also here non-unitary terms emerged. In the next work by Kiefer and Wishman, the authors developed a procedure to redefine the quantum state with a phase transformation in order to make the total Hamiltonian of the system Hermitian, and so to make the non-unitary terms equal to 0. However, we have shown that this procedure is not valid in general due to a requirement of this commutator, which was used as equal to 0, but it is not equal to 0 in the general case. So now I will talk about our proposal for this problem. First of all, we have performed a WKB expansion with a parameter m proportional to the square of the Planck mass, as in the Kiefer work. Since this parameter is a mass over a length, we will have a perturbative expansion, which is valid for particles which have a small mass-component length ratio, when I mean small with respect to this parameter. Then we have performed a Born-Oppenheimer separation, so we have written the wave function into a separable form, a part for the slow gravitational sector, which is here represented by the induced metric h on the hypersurfaces, and a part for the fast matter sector, which has the matter fields and these variables y mu, which I will explain in a moment. Due to the Born-Oppenheimer approximation, we have the fact that the matter part lives at a slower energy scale, so this ratio between the Hamiltonian applied to the matter part and to the gravitational part is small, and we can assume that the gravitational part satisfies its own super-Hamiltonian and super-momentum constraint. And also, we have the fact that the matter part varies slowly with respect to the gravitational variables, so these derivatives are small. This procedure for gravity was used in this work, in these two works. However, we have shown that if we apply the WKB procedure to these works, also here the matter has a non-unitary dynamics. So to avoid this problem, we have used the kinematical action into our model. We have used this term, which was first defined by Kukash, as a way to naturally insert the system constraints into the action. And this term was also used for gravity, for example, in this work. This is the form that we are going to use, which has the variables y mu, which I mentioned before. These variables are the ones that define the parametric equation of the hypersurfaces. So these are deeply linked to the choice of the ADM foliation. This will be important later. We have inserted this term as a fast component into our model. And we observe that the kinematical action allows us to restate the covariance under the choice of ADM foliation for the gravitational background. As I said before, it is deeply linked to the choice of foliation. And then n nu is the deformation vector, which is used in the ADM foliation. These terms also gives us additional contributions to the constraints, because we will have an additional term for the super-Hamiltonian and an additional term for the supermomentum, where pi mu is the momentum which is conjugated to the variables y mu. So the constraints of our model are, for the gravitational wave function, its own super-Hamiltonian and supermomentum constraints without the matter terms and kinematical terms. And in this equation, the single index I, for example, hi, represents a couple of spatial indexes. And the dot in the supermomentum part represents a symbol that we have used for a specific contraction of the indexes. And then also we have, for the total wave function, the total super-Hamiltonian equation with the kinematical term that comes from the kinematical action, and the equation for the supermomentum for the total wave function. And also we have used as an ansatz obviously an exponential wave function for the choice of the WKB expansion. And we have used the sigma functions for the slow gravitational sector and the eta function for the fast matter sector. So what we have found is at the highest order of expansion, an Hamilton-Jacobi equation for the gravity sector with the function sigma 0. So this means that our model gives us the correct gravitational limit. So we obtain the Einstein's equation at the first order of expansion, which is the order m, where only gravity lives. Then at the next order of expansion, we have found a Schrödinger equation for the matter sector, which is here written, where the total Hamiltonian for the matter part is a combination of the super Hamiltonian and super momentum parts integrated over the spatial hypersurfaces. And the time parameter that we have chosen is defined such that these derivatives is here written. So the derivative with respect to the new time variable is given by a linear combination of the terms that come from the kinematical action, because we have pi mu, which is the moment of the kinematical action. The linear coefficients of the combination are the components of the deformation vector and mu, and we also have the integration over the spatial hypersurfaces. The most important point of the expansion is the next order, because we will have the matter dynamics with quantum gravity corrections. This is the equation that we have found, where we have obviously the Schrödinger equation plus some corrective terms. Here I have written more explicitly the contraction which is inside the supermomentum part. And we can see that these correction terms are, first of all, small, because we have the derivative of the fast matter wave function with respect to the gravitational variables, which was assumed small due to the Banach-Number approximation. And these terms are also unitary in our case, because we have the real function sigma 0, which was the action at the highest order that satisfied the Hamilton-Jacobi equation. And we also have the conjugate momenta of the gravitational variables. So in total, these corrective terms are unitary. Then I want to talk about applications in cosmology of this model. So first of all, let me recap what we have found. We have performed an expansion which is valid for matter field whose associated particles have a small energy with respect to the Planck scale, and the corrections to the dynamics of these matter fields are small. However, we can think of possible scenarios to investigate this possible effect, such as the de Sitter phase of the scalar field during inflation, but also the scalar perturbations during inflation, and also possibly the temperature of the Hawking radiation associated to a black hole. All these scenarios are due to the fact that we will have a modified dynamics with the corrective terms. So we have performed the computation for the case of the scalar field in the de Sitter phase. So we have considered an homogeneous scalar field in a specially flat Friedman-Robertson-Walker background. Here is the scalar curvature, and we have a cosmological constant that accounts for the almost constant potential in the de Sitter phase. Since we are working in the homogeneous case, we will make use only of the lapse function of the deformation vector, which is the component n, and which will give us the derivative of our new time parameter with respect to the previous label one. And we will have only the component P0 for the kinematical action part. Then integrating over a fiducial volume, we have obtained the total Hamiltonian for this model, which is here written. And we can see that we have the gravitational term, the matter sector term, and the kinematical action, obviously. Then using another time tau here defined that scales as the cube of the scale factor with respect to the previous one to ease our calculation, we have found the dynamics for the matter wave function key in Fourier space, which is satisfied by this equation. And we have computed the solution for the Fourier transform of key, which is here stated. So we have found a solution for the matter wave function, and I remind that this is valid for the range in which the perturbative expansion is valid. So the momentum k associated to the scale factor will have to be small of order 1/m. So in this slide, I have presented some graphs that we calculated in this case. So in the first row, we have the evolution of the wave function when the corrective term is not present. We have used a Gaussian wave packet, and we have assumed and we have constructed a packet such that the momentum k is small. So there is a small variation with the scale factor, which is very small and almost cannot be seen in these graphs. And in the second row, I have presented the same graphs, but when the corrective term is present. And we can see that there is a slight modification with the evolution in time when alpha approaches 0, and alpha is the logarithm of the scale factor. However, these effects are very, very small, as you can see from the numbers that are on the axis. So finally, I want to relate our model with the procedure of a reference frame fixing. I'm referring to this work by Kukash and Torre, which used a total action which had the gravitational part and a new term. So you can see that there is a similarity with the kinematical action procedure by the same author, Kukash. This new term is used to fix the Gaussian reference frame, which has this component for the metric tensor, by inserting this constraint into the Lagrangian with some Lagrangian multipliers. Also, this action is then rewritten in a parametrized form to recover the covariance, otherwise this constraint would break the covariance. And this is the form that the authors obtain, where x means the spatial coordinates of the Gaussian reference frame, and t is the time coordinate. And this term can be seen as a source term for the gravitational field. This means that the reference system, which is fixed, materializes as an incoherent dust. This is because the stress energy tensor is in this form, the quadric velocity is here defined, and this can be seen from the properties of this stress energy tensor that this is an incoherent dust. The dominant energy condition is satisfied only if the Lagrange multiplier m is positive, and this term used for the matter dynamics allowed the authors to obtain a Schrödinger equation with time t that coincides with the label time t in the Gaussian frame. So the emergent fluid can play the role of clock for quantum matter. We have proved that when applying the WKB expansion also in the parameter m to this scenario, in the mini superspace, we obtain this equation, which has a corrective term, which you can see is of the same form that we obtain with the kinematical action. So this means that the two procedures are equivalent. This is due to the fact that if we work in the mini superspace, we can consider a foliation such that the normal direction only has the 0 component of the force vector. And we have also the same for the kinematical action part. So we will have only the 0 component, and the time derivative of y mu will give us exactly the derivative of t, which will give us n, and which is equal to 1 in the Gaussian reference frame. So these two implementations are equivalent in this case. So just to summarize our work, we have shown that with a Wenzel-Kramer-Brillouin expansion and a Born-Oppenheimer separation, we can use the kinematical action as a clock for the quantum subsystem. This procedure gives us the correct limits of the model and gives us a matter dynamics which is unitary, also including the gravitational correction, which is a difference from the previous work in literature that I mentioned. Also, these corrections that we obtained are small, and we obtained them in a perturbative expansion, but they are in principle detectable. Then the future perspective of our works, which we are working on right now, are the application of this model to the scalar perturbation of the inflation of the field of the inflation. And also, we want to demonstrate the equivalence between the kinematical action procedure and the reference frame fixing procedure that I previously mentioned. And that is all. I think I went fast because I still have a couple of minutes. Thank you.
Thank you very much. Are there any questions? Please raise your hand. Yes, Jan Novak.
Yes, I want to have a question. How big is the effect for tensorial perturbations? I mean, primordial gravitation waves. So, did you have some numerical values, or I mean, how big is the effect? Okay.
Thank you for the question. We still have not investigated that, so I cannot give you a number or an order for these corrections. However, this is also a future perspective that we are considering for our work. Also to compare this with other works in literature that did this calculation with different gravitational corrections. So yes, we are going to compute these corrections.
Thank you.
Thank you.
Thank you. Any other questions? Okay, if not, thank you, the speaker again. Now we have a little problem with our session because Dr. Tawfik actually appeared and he was late because he had a talk on other session. So my proposal would be this. Are you with us, Mr. Tawfik?
Yes, yeah.
Good. So why don't we do the following? Why don't we go ahead with the last talk, which is by Mr. Kinyak Lochan, if I spell it again properly. And then after this talk finished, if you want to present some highlights of your talk, then I hope we're gonna have at least 5 or 10 minutes that you can actually use. The problem is that I was told by the organizer that they are going to switch us off is right at 12:30. So we can try to start your talk, your highlights, and but we are actually taking a risk that perhaps we're gonna be disconnected by the by the authorities. But let's hope for the best, and let's try starting with the scheduled talk by Dr. Lochan. Yes, are you with us? Yes. Hello.
Yes. Hi. Am I audible?
Yes, yes, yes. Please just share your screen. Go ahead with your talk. We start a little bit earlier. You have the standard 20 minutes for plus 5 minutes question time. And then right after that, we will just have highlights of the talk of Dr. Tawfik. Thank you.
Sure, sure. Okay, so please let me know if my slides are visible.
Yes, I see them perfectly well.
Okay, thanks, great. So let me start by thanking the organizers and session chair for giving me this opportunity. And the work I'm going to talk about is reported over here, which is done in collaboration with Henry Colbert at Southampton, Anja Vinante at IFN Trento, and Sandeep Goel at my home institution, ISER Mohali over here. So I'm going to talk about observation of semi-classical signatures in physics through Unruh Debye detectors, and semi-classical signatures in the physics, as we know, are important because typically, as we saw in the previous talk as well, the deviation from semi-classical signatures are the markers of quantum gravity signatures in physics. And apart from cosmology, one more place where you see semi-classical physics at business is in the case of black holes, more particularly black hole radiations, where the semi-classical analysis, famously by Hawking, revealed that the black holes will appear to be a thermal object radiating at temperature given by their masses, and it is the famous Hawking radiation. If we try to induce quantum gravity correction into it, typically there will be thermality will get shifted to a non-thermal spectrum, and there are many versions of quantum gravities where you can try to adapt to black hole evaporation process, and you will be left with a slightly modified spectrum from black hole, and many other works have been done in this. Now, a related, conceptually similar program or avenue is the famously known Unruh effect, which is the flat space effect. It's a divide of any gravity, but it's in flat space where a accelerated observer feels the Minkowski or inertial vacuum to be a thermally populated one. It feels it as if it is moving in thermal environment. That's what that was done way back in 1976. But still, you can argue over there. Suppose there are quantum gravity corrections or non-invariant violation kind of theories, they will dub some non-thermal aspects to even Unruh effect, and the particle moving at constant acceleration we feel is as if they are not perfectly moving in a thermal environment, but slightly deviated atmosphere. So this is the idea where you will try to see how quantum gravity effects can try to bring in correction, which you can try to measure. And this is my brief outline. I will try to start with a very brief summary of quantum vacuum and lessons we learned from general covariance. And then we will try to adapt it to non-inertial motion, just like Unruh observer or Unruh effect does. And a particular lab-friendly case of non-inertial motion would be rotation. We'll try to launch Unruh detector on a rotating trajectory, which is not itself a new thing, but added with two couple of more interesting things: spontaneous emission from Unruh detector and usage of a cavity. With this, we will try to see how the semi-classical effects can be distinguishably taken away from inertial effects of UFT. And in the same spirit, one can visualize the quantum gravity corrections, if there are any, can also be isolated using these two processes, which we are going to talk about. Okay, so when we try to stitch together the concepts of general relativity and concepts of quantum field theory, there are a couple of important lessons we'll learn. First is that because of we are allowed to do general coordinate transformations, the metric as seen by one observer is not necessarily the same as seen by the other observer, because two different observers related by general coordinate transformation will perceive the metric differently. An outcome of that, these two observers will also find that the content of the quantum field which they are living in are also different, because the content of quantum fields is not a covariant aspect, as we will see quickly. So standard quantum field theory, the vacuum is supposed to be only Poincare invariant. Due to Poincare transformation, vacuum changes by no amount, it remains the same. But that is not true under general coordinate transformation. Vacuum is not invariant under general coordinate transformation, and this is the reason where the Hawking radiations come about, where the asymptotic stationary observer visualizes the vacuum of a freely falling observer at the horizon to be a thermally populated state. Just like this, if you calculate the number density as seen by asymptotic observer in the vacuum, as seen by the freely falling observer at the horizon, they will obtain a Planckian spectrum with the temperature decided by the surface gravity of the black hole. And as we discussed, since Unruh effect is also a related concept, the same principle goes into the picture, where the Rindler observers now visualizes, which Rindler observer is one which is constantly accelerating, visualizes the vacuum of the inertial observer to be a thermally populated state with a temperature decided by the acceleration at which it is moving. Okay, so how does this two effect come up? The brief summary of that is that particle content, as we have discussed, is not a covariant object, because to obtain a particle picture of this thing, you have to do a canonical quantization of the field, where you take a time-like surface, where you take a time direction and space-like hypersurface, where you decompose your field modes into and identify positive energy eigenmodes and negative energy eigenmodes. And these AK and AK daggers are excitations of those kind of modes, and which give you particle interpretation. But since you're trying to put general coordinate transformation into this picture, there is no unique way of foliating the space-time with one hypersurface and time-like direction. There can be as many as you wish. So suppose there are two observers. One is foliating the space-time with one choice, and another is another choice, and they are getting two different set of mode functions, U1 and U2 respectively. This overlap of the mode functions U1 and U2 give rise to the famous Boglie-Bow coefficients alpha and beta, where this coefficient beta is of particular importance because it counts the number of particles as seen by the other observer in the vacuum of the first observer. So suppose you take a vacuum of observer 1, which is given by this ket 0, and you ask how many particles the observer 2 finds in this vacuum, that would be given by this expression. Of course, the number of particles of observer as seen by observer 1 in this vacuum will be 0. So beta will be trivially 0 for observer 1, beta will be non-zero for observer 2. Now this is the field theory construct. How to implement it in observation or experiment is given by something known as the Unruh detector, which is considered as an operational device to measure the field content in this, where the quantum mechanical system is coupled to quantum field, and the time evolution of the quantum mechanical system counts the field content. For example, there is a quantum system driven by this total Hamiltonian, where this part is driving the quantum system, this part is for free field, and this is the interaction between the field and the quantum system at hand. Now we will treat this interaction term as a perturbation to the quantum system and the free field theory, and the interaction, this when treated perturbatively, will lead to transition in the quantum mechanical sector. For example, you can take a monopole interaction term where the quantum M is coming from the quantum system block and phi is coming from the field. These two have linear coupling with each other. In this case, the probability of transition from state phi I psi I, where the field is initial configuration phi I, the quantum system is initial configuration psi I, to phi f psi f is given by the transition amplitude is given by this expression, leading to the expression of probability of transition in the quantum system by this. So initially quantum system was in psi I, and finally it lands up in psi f, irrespective of where the field goes. So we have traced over the field configuration. So you will get this expression where you will get a double integration with a Friedman function in picture, the 2-point correlation function at time tau and time tau prime. Tau and tau primes are the rest frames of the particle or the detector at hand. Now, since in the vacuum, the Friedman function is a function of tau minus tau prime only, I can construct a rate of transition. This is the probability of transition. One can construct a rate of transition by taking a time derivative. And you will get this expression where this is just nothing but just the Fourier transform of the Friedman function, which gives the rate of transition. Now, we said that this is an operational device of measuring the field content. So this device would better not register any transition if it is in Minkowski vacuum. That means if you are moving along inertial trajectory, which G is sensitive to, then the detector should better not click. And indeed, this is the picture, because if you put in this inertial trajectory into the game, you will end up getting the transition rate as this expression where and this will vanish because of the positive argument of the delta function, because there are no field modes contributing with negative energy minus capital omega. Capital omega is the energy gap between psi I and psi f of the quantum mechanical system. Okay, so if you are moving inertially, this detector will not click, and it will say that it is a field content of the system is 0 in the Minkowski vacuum or inertial vacuum, which is so far so good. But if you do non-inertial transformation under that precisely gives rise to, if you are start moving on not on inertial trajectory but a constant hyperbolic eternally accelerating trajectory, this rate becomes non-zero, and actually it gives rise to exactly the thermal transition rate. So the accelerated atoms which are launched on eternally accelerating trajectories will undergo transition as if they are moving in a thermal bath. Okay. So now this is the operational way of visualizing how many particles are there vis-a-vis which observers you are talking about. But these effects are typically very tiny. So for a typical quantum system, say hydrogen atom, and you take a typical transition lines over there given by capital omega, the required acceleration to visualize this effect is phenomenally large. That, for example, 1 Kelvin effect, if you want, this is a thermal kind of transition. If you want that it behaves as a system is put in 1 Kelvin temperature bath, then the acceleration required for this process is 10 to the power 21 meters per second square. This is way beyond the reach of any particle accelerators or anything which we can build as of now. So people try to get around with this with various proposals looking at high energy phenomena where particle decay is slightly affected by small temperature physics, or people look at quantum entanglement over here, or people look at thermal querying. There are so many approaches which people try to come across because of this kind of things. All these effects are very tiny. People try to zoom into this tiny effects and try to see which, if anything, can be done. Many such attempts have been nicely reviewed in this living review by Crispino and Higuchi. And but the bottom line is that with today's technology, even this kind of effect is not visualizable in any realistic systems. Similarly, for black holes, the same kind of physics goes through, and the bottom line comment is the Hawking radiation as seen for a typical black hole system would be extremely small, and it would be very difficult to have a direct signature or direct measurement of the black hole emission or the UV effect in any kind of setting. So this is very difficult task, and from this itself we have to filter out the quantum gravity signature by looking at semi-classicals, by taking out the semi-classical thing. So we should have a good handle on semi-classical thing operationally before we can clearly filter out what is the quantum gravity signatures in that. Okay, so that's what we would want to do, and we will try to change this picture where the experimental verification of this frame transformation leading to different kind of particle content is potentially visualizable in lab setting or something. So to do so, what we propose is that, as we discussed, the Rindler observer finds itself in a thermal background, but Rindler acceleration or Rindler trajectory is not the only possible accelerated observer's trajectory. There is this is just a special trajectory where the observer is moving on a constant acceleration trajectory for all times. In principle, any non-inertial motion will change the vacuum, because vacuum is not invariant under general coordinate transformation. As an effect, Friedman function, the 2-point correlator function as we saw, will also change. And once that changes, the rate of change, rate of transition or transition rate itself will have a effect on that. So there are two kinds of non-inertial motion. One, where the Bogly-Bo coefficient beta is non-zero, just like a Rindler observer. And there is another kind of sets of non-inertial motion where Bogly-Bo coefficients are 0. For example, a rotating observer, but still the detector clicks because the Friedman function is changing. With change of Friedman function is not necessary for Bogly-Bow coefficient turning off or on, but changing Whitman function is necessary for a detector to click. So as far as the detector or the operational viewpoint of particle content is considered, we will adopt the notion if the detector clicks, the particle content of the field has changed under non-inertial motion. This is the standard Unruh-David approach, Unruh-David detector approach one would take. So with this, we'll launch the detector. With this insight in hand, we launch this Unruh-David detector on a circular trajectory. We are considering the detector as a two-level quantum system with 5 ground state and excited state, the wave functions given like this. And we are moving in the XY plane circularly, XZ plane rather, about the Y-axis. The space-time metric as seen by the rotating detector is given by this expression. And the interaction between the quantum mechanical system and the background field, which we take to be the electric field. So the background field phi is replaced by electric field over here, is given by this. Now we have taken only those kind of states where the transient dipole moments are surviving only for the y component. So I'm just writing y component. In principle, there will be other components in this general covariant sum, but all those components will drop off because of the choice of state at hand. So, and since it's a covariant way of writing this, I can bring this interaction term down to the lab frame itself, because in rotating frame and lab frame, the times are just rescaled by this factor. So we will have this interaction term as seen in the lab frame. So there is a detector moving circularly in the presence of electric field. By the presence, I mean that it's interacting with electric field. I have not said what is the state of the electric field. I'm going to put the electric field in vacuum. There is no electric field applied. Right? But
I'm afraid we cannot really hear you very well. So please try to repeat the last couple of sentences.
Hello, is this better?
Yes, now it's better. Yes, please continue.
Okay. So I was just stressing that in the rest frame of the detector, the interaction term is this. While since it's a vector field and you have to do general coordinate transformation, you have to be careful about how the vector field transforms under those. So under this transformation, this electric field as seen by the rotating detector would transform into the combination of electric and magnetic field as seen by the lab observer. So now you compare the interaction term just like we had before. This is like effective M and this is like an effective phi for us. Now, as we knew that for the transition rate, the Fourier transform of the 2-point function of the field phi is under the action. So here the phi is combination of electric and magnetic field. So we will get, we will have to do a Fourier transform of 2-point function of electric or magnetic kind of interaction term. There will be cross term E and D, which will drop off in the calculation, which I am not showing over here. Only surviving terms will be of this nature, which you can calculate from basic of quantum electrodynamics. And R over T, RT minus is just the trajectory, the 2 points on the trajectory moving on a circular trajectory as over here. So R of minus T is any vector connecting from origin to periphery of the circle. Now all these computations are slightly lengthy, but very trivial to do. And one can get away to the transition rate calculation from here. Now you see, this is a lengthy expression. I think, sorry for the small fonts, because it was a slightly bigger expression. So the first term over here is the purely inertial contribution. The second term is purely non-inertial contribution. And there is a cross term which will come because the transition amplitude itself gets summed over in inertial and non-inertial. So mod square will have a mixed term as well. And there will be higher order resonances as well. Now, you see, this is not a very helpful picture as of now, because again, this positivity of the delta functions argument will kill this term, kill many of these terms. Actually, only 2 terms in the first 3, only 2 terms here and here have a potential to survive when the rotational frequency omega becomes larger than the atomic transition gap. Unless you are doing that, if your rotation frequency is smaller than that, there is no transition at all. There is a possibility only if you cross certain threshold. This is not helpful as of now, but it gives a new insight that apart from the inertial term, the non-inertial terms do not come at the same transition frequency. They have slightly shifted transition frequency because of their rotations, omega plus omega and omega minus omega. Okay. Now this can be utilized in the schemes we were thinking about.
that we will introduce the spontaneous emission process, where you do not ask the question of the detector going from the ground to excited, but you ask the question the reverse way. Suppose your detector is initially in excited state, and what is the probability of getting into the ground state? So there, this E and G will flip their roles. Capital omega, which was the energy gap, will flip to minus omega, and everything will go as smooth as before. And all the calculations go with the identification, the capital omega going to minus capital omega. So now this long-term response compared to this capital omega will shift to this thing minus. So you will get this expression. Here you see the inertial contribution becomes this, which is non-zero now. Non-zero because of omega k mode is available at capital omega. This is the inertial contribution, which we know as a spontaneous emission in hydrogen atom.
Excuse me, you have a couple of minutes left, so please go to conclusions. Thank you.
Yeah, so there are non-inertial terms, only thing which are all also non-zero, but they are now at shifted frequency. The mode function at shifted frequency will start contributing. Okay, now one more effect we will try to put it into it. So typically, this is sensitive to the density of states calculations. So you see rho of k is the density of field state, which is coming over here. In free space, density of state is going as frequency squared, and the spontaneous emission rate, the inertial term in this picture, is proportional to capital omega q because of the delta function over here and the rho k going as omega k square, which is this. Typically, this is the spontaneous emission calculation what one would do in any QT book. This is also very small because the frequency involved is very small. But what Purcell in 1946 suggested a way out of it, to use a cavity, where a cavity, inside a cavity, the density of state is not this, but replaced by a Lorentzian. And when the cavity is tuned at capital omega, inside the cavity, the spontaneous emission rate is independent of capital omega and becomes sensitive to the quality factor. So the smallness of capital omega is taken care of. We thought of implementing the same for non-inertial term, which we're coming into that. And then we are using the rho omega as the cavity thing, and we isolate the total only non-inertial term, subtracting out the cavity inertial picture contribution out of it, which goes by this expression, density of states derivative, and things will come about. Putting the Lorentzian thing in, the cavity Lorentzian thing in itself, the purely non-inertial signature, again as before, gets scaled with Q, and it becomes independent of the energy, the frequency of the transition. Now this rapidly rises with capital Q. Now, it is for a detector, it is for a cavity which is resonating at the new transition lines. So if we plot this as a diagram, this is the cavity resonance frequency, this is the inertial term, blue is the inertial term, red is the non-inertial term. Most of the time, the inertial term is super dominant. Only around this cavity resonance frequency is tuned with the rotational frequency, you will find that it is a slightly dominating over there. And actually, we can put down numbers. With these number estimates, one can find out the cavity transition. Inside the cavity, the transition rate is 10 to the power minus 7, with the Q, which is the ratio of inertial to non-inertial to inertial, that is 10 to the power 4. Meaning there is only one part in 10 to the power 4 where the inertial signature is present. So that is a purely non-inertial signature. All these things are not just a instrumental number. Actually, all these numbers are independently achieved in different kind of settings. So one can put all these things together and propose a cavity kind of experiment like this, where a LC kind of cavity where you put a rotating atom, and you can obtain purely non-inertial signature at a maximum acceleration not only of 10 to the power 12 meter per second square. Here, the non-inertial signature is 10 to the power 4 times larger than the inertial signature. Compare this with the Ungu case where 1 Kelvin effect was 10 to the power 21 meter per second square acceleration. So just to conclude over here, so we see that introduction of cavity allows us to use the additional transition lines moved in by the non-inertial motion. The similar thing can be done for curvature physics, where the third spacetime physics, where curvature scale can be tuned in resonance with the cavity. And once you tune the cavity at those particular resonance points, all other signals, inertial as well as driving force and whatnot, will get suppressed. So the observation will be free of noise. And there will be quite distinguishable signature because the transition is happening at a new transition frequency, not at the atomic gap transition level. This can be implemented not only for non-inertial rotation motion, but also for those where beta is non-zero, just like Rindler trajectory or any general trajectory. These two preprints are more into elaborate into this. One is by the group of Kemp and other is with our group only. So the idea is the cavity and with cavity and spontaneous emission or stimulated emission, one can isolate clearly the semi-classical signatures. But if that can be done for semi-classical signature, there is a hope for that it can be done for quantum gravity signatures as well, because they will come with their independent scales as well. And one can, in principle, apply the same aspects to isolate them completely. So I think I will end here and will be happy to take questions.
Thank you very much for a nice talk. Are there any questions? Jan Novak, please.
Yes, please. Why this is a pure, I guess, effect of quantum field theory in curved background? Where is the quantum gravity? I mean, I don't see.
So right now there is no quantum gravity. What I'm trying to say is that even the quantum field theory encoded space-time signatures are difficult to isolate. The principles I'm suggesting is that if one can isolate the signatures of curved space QFT with using cavity, one can do the same for the quantum gravity thing, because as quantum gravity will be the correction over the semi-classical thing. So I'm trying to isolate the semi-classical aspects observationally or operationally.
Okay,
Thank you. Are there any other questions? Okay, if not, we still have 7 minutes till the end of our session. So we have Dr. Tawfik has certainly 7 minutes for his presentation. You can just try to go ahead, hoping that no one is interrupting you. Given that we will probably run out after schedule at this moment, why don't you try to make your actually to spell out your major point within something like 10 minutes, so that we still have time for perhaps 1 or 2 questions. All right. You should unmute your microphone. I cannot hear you. So please unmute your microphone, and also if you have a camera,
hello.
please.
Hello,
please.
hello.
Yes.
Yes. Okay.
And please switch on your camera if you can.
Okay. How can do this? You see my screen at least.
Yes, I can see
Okay.
a screen,
Okay.
but please make it full screen presentation.
Full screen, sure.
I think that if you click
okay,
slide,
I'm going to
just click slide.
Hello?
Oh yeah, now it works. Thank you.
Yeah.
Go ahead.
Yeah. Okay. The title is Non-Symmetric Metric Tensor as an Approach for Quantum Gravity. The main problem is that we know that the Einstein field equation relates classical geometry with the quantized energy momentum tensor. My proposal here is to try to understand whether the minimal length, as proposed by the GOP, the generalized uncertainty principle, could enable us with a kind of quantization, if not a kind of discretization of the space. In doing this, I'm going to confront these results with the Einstein field equation. I'm starting here with the metric tensor itself, with the line element, and with the geodesic equations. Problem. Sorry. Now. Okay. Also
everything
now
seems to work fine.
Very good. The QP minimal length was proposed a long time by Kempf, Monjano, and Martinez, and you can see accordingly that the minimum length is in the order of the square root of h bar g, the gravitational constant, divided by c cubed. There are various proposals for the QP million. For example, Giori also proposed another one based on quantum deformation of the Poincare algebra, and accordingly the minimum length takes this form, which is the square root of gamma 0. Gamma is the GOP parameter, and also this beta appeared in previous expression are also both are also GOP parameters, which could be determined from other experiment, thought experiment, or even from inspired by the GOP, the canonical commutation relation for quantum operator can be expressed in this way. And also similarly, we can express also the the corresponding commutation relation for the operators themselves. The main idea is that the non-commutation relation can be included in the space-time geometry through enlarging Minkowski manifold to an 8-dimensional space-time. For instance, this is the x to 8, x to a, and a goes from 0 to 7, the 8-dimensional quantity, and when we do a line metric in the 4-dimensional space, this is the left-hand side, and the modified Minkowski line space. Almost the same where we have here mu, and here we have AB, and AB, as I said, AB and capital or small goes from 0 to 7, and the Greek letters mu, nu, lambda goes from 0 to 3. Coming back from 8-dimensional, the 4-dimensional space, we use this expression, and accordingly we can have a kind of expression for the metric tensor G mu nu tilde, which is given by this expression, which could be summarized in the far right-hand side, square 1 plus beta x double dot lambda all multiplied by G mu nu, the uncorrected one. This means that we get some correction to the G mu nu. And in flat space, we can express also G mu nu in this expression, where H mu nu equals beta lambda double dot lambda x double dot lambda and x double dot lambda eta mu nu. The same can also be done for metric, and you can see here the ds tilde squared equals ds tilde squared multiplied by this bracket 1 plus beta squared lambda double dot lambda x double dot lambda and x double dot lambda and so on. This is a correction term according to the GOP approach. Also, we can equation in a flat space. We get this expression which contains the additional parameters, and in curvature space we have a very complicated expression for the geodesic equation, where the various parameters below. What we have right now, we can conclude, at least from the geodesic equation, that our result means that not only acceleration x double dot of the test particle in the gravitational field is increased. If you can review again this expression for the geodesic equation, you have higher derivatives of the x, not only the second one. Namely, we have snap, we have choice, and we have even jerk. The acceleration, which already have observed in astrophysical observation and awarded a Nobel Prize a couple of years ago, now we have some approach to explain the origin of the expanding acceleration. Means that we are, the space is not accelerated, but also has higher order derivative of the acceleration and so on. Jerk and the snap give, jerk, for example, gives the change of the force acting on that test particle, and the snap is resulted from the change of the jerk itself. Both quantities are finite when the vibration occurs, especially for multi-resonant modes, and for sudden transition between different radii of the curvature. To summarize here, these are the approach of the GOP, where the operator x and p are given by this expression, where beta appears here as a correction due to the GOP. When we apply this to geometric tensor, we have some correction in form of beta square x double dot x double dot. And also the line metric also gets another expression or another correction, and this equation, if I limit for the flat space, we have in this form are for the curved space we have in this form. As for the title of the talk, which goes to the symmetric properties of the general of the metric tensor, I can just tell you that these calculations are still under.
I'm sorry, we lost you.
Yes.
Yes, please continue, because we lost you for a second.
Yeah. I'm finished. At least I have to summarize my talk. That the metric tensor obtained even for the QB remains symmetric as the original one. This is the main conclusion of my talk.
Okay, thank you very much for your talk. I'm sorry that it was necessarily so short. I think that we're still on, so if there are any questions, please please ask.
Yes, sure.
Okay, I don't see any questions, so thank you everyone for taking part in this second session of quantum gravity phenomenology session, and we meet again tomorrow at 9:30. Goodbye.
Bye-bye.
Thank you. Goodbye.